Good morning everyone. I am Dr. Pankaj Kumar Mishra, Professor in University Teaching Department, Chhattisgarh Swami Vivekanand Technical University, Bhilai. I am thrilled to welcome you to today's lecture on comparison of various digital modulation techniques. This lecture is a core part of our course Fundamentals of Communication System and its application. Our focus today will be on digital modulation techniques which are essential for modern communication systems. Digital modulation is a fundamental aspect of digital communication system. It involves modifying a carrier signal in a way that reflects the information being transmitted. This process is crucial for ensuring that data is transmitted efficiently, accurately and effectively over communication channels. Throughout this lecture, we will explore various digital modulation techniques including amplitude shift keying, frequency shift keying, phase shift keying, quadrature amplitude modulation. Each of these techniques has its own unique characteristics, advantages and disadvantages. By the end of this lecture, you will have a comprehensive understanding of these modulation techniques, their applications and how they compare to one another. Overview of modulation in communication system. What is modulation? Modulation is a process used in communication system to transmit data over a channel. It involves varying one or more characteristics of a carrier signal such as its amplitude, frequency or phase in accordance with the data signal. The carrier signal serves as a medium to carry the information signal from the transmitter to the receiver. In essence, modulation helps in adapting the data signal for transmission over a medium such as air, optical fiber or cables. Without modulation, transmitting data over long distance would be inefficient and prone to interference. Analog versus digital modulation. In early days of communication systems, analog modulation techniques such as an amplitude modulation and frequency modulation were predominantly used. These techniques involve varying the amplitude or frequency of the carrier signal in accordance with an analog signal. While analog modulation was effective for its time, it has limitation in terms of noise resistance, bandwidth efficiency and data integrity. Digital modulation on the other hand involves modulating the carrier signal based on binary data, that is zeros and ones. Digital modulation techniques offer several advantages over their analog counterparts. Higher noise immunity, digital signals are less affected by the noise and interference. Improved data integrity, error detection and correction techniques can be incorporated. Efficient bandwidth uses. Digital modulation techniques allow for more efficient use of the available bandwidth. Evaluation of digital modulation. The transition from analog to digital modulation began in mid 20th century with the advent of digital communication technologies. This shift was driven by the need for more efficient, reliable and scalable communication systems. Early digital modulation techniques were relatively simple, but as technology advanced, more sophisticated techniques were developed to meet the growing demands for higher data rates and improved performance. Categories of digital modulation techniques. Digital modulation techniques can be broadly categorized based on how they vary the carrier signal. The primary categories are amplitude shift keying, the first one, frequency shift keying, second one, third one is phase shift keying. Each category includes various techniques that differs in their modulation methods, performance characteristics. We will explore each category in detail, examining their advantages, disadvantages and applications and compare them. Detailed overview and comparison of digital modulation techniques. First one is amplitude shift keying. Amplitude shift keying is one of the simplest digital modulation techniques. In ASK, the amplitude of the carrier signal is varied in accordance with the data signal. In binary ASK, the carrier signal has two distinct amplitude levels, one for representing binary 1 and another for binary 0. ASK can be visualized as a waveform where the amplitude of the carrier signal changes according to the binary data being transmitted. For example, if the data signal is 1, the carrier signal might have a high amplitude, and if the data signal is 0, the amplitude might be low or 0. The advantage of ASK: simple implementation. ASK is a straightforward to implement with basic electronics component, making it cost effective and easy to design. Power efficiency: in certain scenarios, ASK can be power efficiently, especially when the carrier signal is turned off during the transmission of binary 0. Disadvantage of ASK: susceptibility to noise. ASK is highly susceptible to amplitude noise. Variations in amplitude caused by noise can lead to errors in data interpretation. Limited bandwidth efficiency: ASK generally requires more bandwidth compared to the modulation schemes, which can limit its data transmission capacity. Application of ASK in optical fiber communication. ASK is used in optical fiber systems where the intensity of light is modulated to transmit data. RFID system, radio frequency identification systems, use ASK for low cost, low power communication. Infrared communication: ASK is employed in infrared communication systems such as remote controls. Summary of ASK: amplitude shift keying is simple and easy to implement modulation techniques. While it is cost effective and power efficient, it is less robust against noise and has limited bandwidth efficiency. ASK is best suited for low data rates application where noise is minimal. Frequency shift keying: frequency shift keying is a modulation techniques where the frequency of the carrier signal is varied according to the data signal. In binary FSK, two different frequencies are used to represent binary 1 and 0. The carrier signals switches between these frequencies based on data being transmitted. Variants of FSK: minimum shift keying. MSK is variant of FSK that minimizes the frequency shift, resulting in better spectral efficiency and reduced bandwidth requirements. Gaussian minimum shift keying. GMSK: GMSK uses a Gaussian filter to smooth the frequency transition, reducing sidebands interference and improving spectral efficiency. Advantages of FSK: robustness to noise. FSK is more resistant to noise and interference compared to ASK, as changes in frequency are less affected by amplitude variation. Spectral efficiency: variants such as MSK and GMSK provide better spectral efficiency compared to traditional FSK, making them suitable for high data rate. Disadvantage of FSK: complexity. FSK modulation and demodulation involve more complex circuitry compared to ASK, which can increase system complexity and cost. Power consumption: FSK can be less power efficient due to continuous transmission of carrier signal, leading to higher power consumption. Application of FSK: telemetry system. FSK is widely used in telemetry system for transmitting data over long distance in noisy environments. Wireless communication. Older wireless communication systems, including some early cellular networks and wireless data modems, used FSK for reliable data transmission. Radio communication. FSK is employed in radio communication systems where amplitude distortion is prevalent. Summary of FSK: frequency shift keying is a robust modulation techniques that performs well in noisy environments, while it provides better noise resistance and spectral efficiency compared to ASK. It involves increased complexity and power consumption. Now come to the phase shift keying, third one. Phase shift keying is a modulation technique where the phase of the carrier signal is varied based on data signals, and in binary PSK the carrier signal shift between two phases angles to represent binary 1 and binary 0. This technique is known for its power efficiency and resistance to amplitude noise. Variants of PSK: quadrature phase shift keying QPSK. QPSK uses 4 phase angles to represent 2 bits per symbol, effectively doubling the data rate compared to BPSK. Higher order PSK techniques such as 8 PSK and 16 PSK use more phase angles to represent multiple bits per symbol, achieving higher data rates but with increased sensitivity to phase noise. Advantages of PSK: power efficiency. PSK maintains a constant amplitude, making it ideal for power constrained environments where signal strength is concerned. Robustness to amplitude noise. Since the information is encoded in the phase of the signal, PSK is less affected by variations in amplitude. Disadvantages of PSK: complexity. The modulation and demodulation process for PSK can be complex, requiring sophisticated signal processing technique. Phase noise sensitivity. Higher order PSK techniques are more susceptible to phase noise, which can degrade performance in certain conditions. Application of PSK: first one is in satellite communication. PSK is widely used in satellite communication system due to its power, efficiency and robustness. Wi-Fi: higher order PSK techniques such as QPSK are used in Wi-Fi standards to achieve high data rates. RFID systems: PSK is employed in RFID systems for reliable data transmission in various applications. The summary of PSK: phase shift keying offers power efficiency and resistance to amplitude noise, making it suitable for various applications including satellite communication and Wi-Fi. However, it can be complex and sensitive to phase noise, particularly in higher order variants. Now come to the quadrature amplitude modulation. Basically, the quadrature amplitude modulation combines amplitude and phase modulation to transmit data. In quadrature amplitude modulation, both the amplitude and phase of the carrier signal are varied to represent multiple bits per symbol. Quadrature amplitude modulation is widely used in digital communication systems due to its ability to achieve high data rates. Variants of quadrature amplitude modulation: 16 QAM represents 16 different symbols, each corresponding to a unique combination of amplitude and phase, allowing for 4 bits per symbol. 64 QM represents 64 symbols, providing even higher data rates with 6 bits per symbol. This technique is commonly used in broadband communication system. Advantages of QAM: high data rate. QAM can achieve very high data rates by transmitting multiple bits per symbol, making it suitable for high bandwidth applications. Efficient bandwidth uses: QAM allows for efficient use of available bandwidth, optimizing data transmission and reducing spectral occupancy. Disadvantages of QAM: susceptibility to noise. Higher order QAM is more sensitive to noise and interference, which can lead to increased error rates in noisy environment. Complexity: the modulation and demodulation processes for QAM are complex, requiring advanced signal processing techniques and precise synchronization. Application of QAM: digital TV and cable modem. QAM is used in digital television and cable modems to deliver high quality video and data services. Broadband internet: QAM is employed in broadband internet system to achieve high speed data transmission. Now, in wireless communication, advanced QAM techniques are used in modern wireless communication systems, including 4G and 5G networks. The summary of quadrature amplitude modulation. The quadrature amplitude modulation offers high data rates and efficient bandwidth uses, making it ideal for broadband and high speed communication systems. However, it is more susceptible to noise and interference and requires complex signal processing. Now, come to the detailed comparison of digital modulation techniques. To provide a thorough understanding of digital modulation techniques, it is important to compare them across several dimensions. This sections will focus on the key criteria, that is bandwidth efficiency, power efficiency, noise immunity, complexity and performance matrices. First, the bandwidth efficiency. Bandwidth efficiency measures how effectively a modulation scheme uses the available bandwidth to transmit data. It is often expressed in bits per hertz. Amplitude shift keying. Bandwidth efficiency in ASK generally requires a bandwidth of twice the symbol rate for binary ASK, making it less bandwidth efficient compared to more advanced techniques. For instance, in binary ASK, the bandwidth is needed is approximately twice times the bit rate. Application context. Due to its low bandwidth efficiency, ASK is more susceptible for low speed communication application where simplicity and cost are prioritized. Frequency shift keying. Bandwidth efficiency. FSK requires a bandwidth that is typically greater than symbol rate. Binary FSK, for example, has a bandwidth of about twice the frequency deviation. Variants like minimum shift keying offer improved bandwidth efficiency by minimizing the frequency deviation. Application context. FSK used in applications where the resistance to amplitude noise is important, such as telemetry systems, but it is less efficient in terms of bandwidth compared to more advanced modulation techniques. Now, phase shift keying. For bandwidth efficiency, PSK offers higher bandwidth efficiency than ASK and FSK. Binary PSK has a bandwidth that is equal to the bit rate, while higher order PSK schemes like quadrature PSK can transmit 2 bits per symbol with the same bandwidth. Application context. PSK is widely used in digital communication systems where efficient bandwidth utilization is critical, such as in satellite and wireless communication system. Now, quadrature amplitude modulation. For that bandwidth efficiency, QAM provides the highest bandwidth efficiency among the discussed techniques. For example, 16 QAM can transmit 4 bits per symbol and 64 QAM can transmit 6 bits per symbol, making it suitable for high speed data application. QAM is ideal for broadband applications including digital, TV, cable modems and high speed internet, where high data rates and efficient bandwidth uses are essential. Now, come to the second point, that is power efficiency. Power efficiency is a crucial for battery operated devices and systems where power consumptions needed to be minimized. In ASK, power efficiency can be power efficient, especially when the carrier signal is turned off during the transmission of binary 0. However, ASK's performance can be adversely affected by noise, leading to potential increases in power consumption to maintain signal integrity. ASK is used in low power, low cost application like RFID and infrared communication, where simplicity and cost outweigh power efficiency concern. Now, in FSK, the power efficiency generally consumes more power due to continuous carrier transmission. However, it is more power efficient than ASK in environments with significant amplitude noise. Application context. FSK is suitable for systems where noise resistance is more critical than power consumption, such as in telemetry and some wireless communication system. Now, come to the PSK. In PSK, power efficiency offers good power efficiency due to its constant amplitude nature. The amplitude involves varying the phase of the carrier, which does not affect the amplitude. PSK is used in application where power efficiency is important, such as in satellite communication and certain wireless technology. Quadrature amplitude modulation. The power efficiency in QAM varies depending on the modulation order and signal processing requirements. Higher order QAM techniques can be less power efficient due to increased complexity and signal processing needs. QAM is used in high speed data communication systems where high data rates are prioritized over power efficiency, such as in broadband internet and digital TV. Now, come to the second one, that is noise immunity. Noise immunity measures a modulation technique's ability to withstand interference and maintain data integrity. In ASK, noise immunity is highly susceptible to noise, particularly amplitude noise. Variations in amplitude caused by noise can lead to errors in data interpretation. ASK is less susceptible for noisy environments, but can be used effectively in controlled or low noise applications. In FSK, noise immunity is more resistant to amplitude noise compared to ASK. Changes in frequency are less affected by amplitude variations, making FSK more robust in noisy conditions. FSK is used in environments with significant noise and interference, such as in telemetry and some radio communication system. In PSK, noise immunity offers high noise immunity due to its reliance on phase variations. The technique is less affected by amplitude noise and is more robust in challenging conditions. PSK is well suited for environments where noise is concerned, such as in satellite communication and high speed data transmission. In QAM, noise immunity decreases with higher modulation orders, while lower order QAM provides reasonable noise resistance. High order QAM is more susceptible to noise and interference. QAM is used in high speed communication system where noise and interference management is critical and advanced error correction techniques are employed to maintain performance. Complexity. ASK is the simplest of the modulation techniques with a straightforward circuitry for both modulation and demodulation. Its simplicity makes it cost effective and easy to implement. Due to its low complexity, ASK is used in applications where ease of implementation is a priority. Frequency shift keying complexity. FSK involves more complex circuitry compared to ASK due to the need for frequency generation and detection, while more complex FSK remains relatively straightforward. FSK is chosen for applications where noise resistance is more crucial than simplicity, but where complexity is still manageable. Phase shift keying complexity. PSK requires sophisticated signal processing for phase detection and demodulation. Higher order PSK techniques introduce additional complexity in terms of phase tracking and synchronization. PSK used in advanced communication systems where the benefits of its complexity, such as improved noise immunity and bandwidth efficiency, outweigh the design challenges. QAM quadrature amplitude modulation complexity. QAM is the most complex of the discussed techniques, involve both the amplitude and phase modulation. The complexity includes signal processing, synchronization and precise demodulation techniques. QAM is used in high speed communication system where the benefits of high data rates and efficient bandwidth usage justify the increased complexity. Now, come to the performance matrices. Performance matrices such as bit error rate, signal to noise ratio and spectral efficiency provide insights into the effectiveness of the modulation technique. First, bit error rate. ASK typical has a higher bit error rate in noisy environments due to its sensitivity to amplitude variance. BER, that is bit error rate, increases significantly as noise level rise. FSK shows a lower bit error rate compared to ASK, especially in environments with amplitude noise. Variants like MSK and GMSK improve performance further. PSK provides a low BER due to its resistance to amplitude noise, but higher order PSK may suffer from increased BER due to phase noise. QAM BER can be high for higher order QAM, particularly in noisy conditions. Advanced error correction techniques are often required to maintain acceptable BER levels. Now, come to the signal to noise ratio, that is SNR. ASK requires a higher SNR to achieve reliable communication, especially in noisy environments. SNR directly impacts the performance of ASK. FSK performance better in lower SNR condition compared to ASK, with variants like MSK providing improved performance in challenging SNR scenarios. PSK maintains good performance at lower SNR levels, with higher order PSK requiring higher SNR for optimal performance. QAM higher order QAM requires a high SNR to achieve reliable data transmission. Increased data rates come at the cost of higher sensitivity to noise. Now, next one, that is a spectral efficiency. ASK has a lower spectral efficiency due to its broader bandwidth requirements. It is less efficient compared to modern modulation techniques. FSK offers moderate spectral efficiency with variants like MSK and GMSK providing better performance in terms of bandwidth utilization. PSK provides good spectral efficiency, particularly in higher order PSK schemes like QPSK, which can transmit multiple bits per symbol. QAM exhibits the higher spectral efficiency by transmitting multiple bits per symbol. Higher order QAM techniques allow for very efficient use of bandwidth, making them ideal for high speed data application. In conclusion, digital modulation techniques play a vital role in modern communication systems. Understanding the characteristics, advantages and disadvantages of ASK, FSK, PSK and QAM is crucial for designing effective and efficient communication system. Each technique offers unique benefits and trade-off impacting data transmission system performance and application suitability. Digital modulation has evolved significantly, leading to advanced techniques that meet the demand of high speed reliable communication. As technology continues to advance, new modulation schemes and improvements will further enhance communication capabilities and performance. Thank you for joining today's lecture. I hope you have gained valuable insights into digital modulation techniques. Thank you all.